and a little bit about the sun, because if we didn't have the Earth, we wouldn't have any of our sources of energy, and obviously if we didn't have the sun, we wouldn't have some of our future sources and our renewable energies. So, let's see. Stand back here. The Earth has, when the Earth first formed, it had two sources of heat. And one source of heat was from the initial accretion of matter from the universe as it was starting out. And once the matter accreted in the form of this ball of material that we now call Earth, the heavier elements started to sink down to the center, and so frictional heat was generated as different layers of the Earth started to form. The second source of heat is that a number of the elements, some of the elements in the Earth are radioactive, which means they have some excess energy. So they're constantly trying to get rid of this excess energy because they're unstable in that form and become more stable forms of themselves or another element. And there were many more radioactive elements in the Earth when it first started out, over here, 4.5 billion years ago. And the concentration of those elements is declining, but they're still with us, and they're still decaying, and they're still generating heat. So the process of the combination of the two sources of heat is what the giving off of that heat from the Earth as it's been cooling is what's generated the Earth as we know today. So the surface of the Earth on average is about 14 degrees Celsius. And the center of the Earth, it's controversial, but it's somewhere around 6,000 degrees Celsius. Okay? So if we think of the second law, heat has to move from the hot areas to the cooler areas. So heat is coming out of the center of the Earth to the surface of the Earth constantly. And the main source today, again, are the radioactive elements that are decaying. So the heat that's coming out of the Earth has created different layers to the Earth. There's a central core that's largely iron with some nickel in it, and it's solid. There's an outer core, which is liquid iron, mostly. There's an area called the mantle here, which is a solid, but it flows. So this would be like ice that's flowing, or if you had silly putty, I should have brought my silly putty, I forgot. You take silly putty, you put it on the desktop, and after a while you see that it flows. So that's what the mantle's like. And then the crust is a very thin layer on the outside that's rigid. Okay. As the Earth was cooling, it started off being nearly completely molten or melted. It started to cool, and the very surface became hard and brittle. And then over time, because the heat was still being generated from deep within the Earth, the heat was moving upwards to the surface, and it was moving up in different places, as represented by these different red lines. And it was causing different areas of the surface of the Earth that were brittle to move around on the surface. They were moving around on this layer of the mantle. So the easiest way to think about that is to think of your lava lamp, which in my day was popular, but I think has made a comeback recently. And so what's going on in a lava lamp? What's down here in this part? A light bulb, okay. What's the yellow and then this kind of brownish material? What? Does anybody know how it works?
Wax.
Some kinds of waxy materials, okay, that get heated up by the light bulb, but they heat up differently. They have different properties. And one will heat up and expand a little more, and it rises through the other one. And when it gets to the top, this is a glass, like a glass container that it's moving up through. And at the top, you have a little metal cap. What's the metal cap there for? It helps the heat get out and go into the air, right? The heat's being transferred out. So it gets to the top, it cools, and when it cools, it contracts, and it becomes more dense, and it sinks back down, and the cycle starts over again. So this is basically the way the Earth is behaving in a very simplistic viewpoint. So if we look at the layers of the Earth, we see that there are different ways to transfer the heat out, different physical ways. So one way is conduction. So this is what Professor Hoffman just talked about, where you have something hot the heat is being moved from the place where it's hot to a place where it's cold. So there's no material moving, right? It's just the heat energy itself. It's when something's hot, the atoms are, did I do that? I don't know. I might have hit something wrong. When something's hot, right, the heat is making the atoms vibrate. So that energy gets transferred to the next set of atoms next to it, and then they start vibrating, and then these stop moving so fast, okay? Remember what was on the top? I had the coffee cup at the bottom. What was the cup on the top? Did anybody catch that? It had spilled. Okay, so that's another way to transfer heat. It's by the physical motion of the material. The hot material moves from this place to this place, not just the energy. And then the one in the middle was going to show you the process of convection. So convection is a way to transfer heat that involves both motion and the vibrational part, kind of together. Think of it that way. I don't remember what my next slide is.
But maybe we take a slight break?
We can take a break. Okay, let's take a break. Physical motion of the coffee is carrying the heat. And then convection is, think of it as a combination of the two. There's physical motion and there's also effectively conduction. So deep down in the earth, at the core, the solid core, where it's really hot, in fact, as hot as the surface of the sun, the heat is being conducted upward to the outer liquid core, and because it's liquid, it's convecting. So let's look at, let me finish that first. And then the convection in the outer liquid core causes this mantle, remember, which is solid but behaves plastically to start convecting. And that carries heat up to the surface where it's conducted through the crust for the most part. And every once in a while, this is a volcano here, there's some advection, actual physical motion of lava coming up that's carrying the heat. So let's look at convection in the coffee cup here, which I'm sure you all did this morning, but you were probably too sleepy to realize that's what you were looking at. This is solar response. Music goes with it. So convection. So you see these darker areas? Think of those as tectonic plates at the surface of the earth. They're growing, they're moving around, they're sinking, okay? How many of you have actually had geology classes? Some, okay. All right. So, convection, let me go back. Convection, okay, basically brings the hot material up, and the top of the crust is like the coffee cup. So it's different tectonic plates that are moving around. And these plates, over the history of the Earth, have formed, disappeared by sinking. They cool down, they sink beneath other plates, they get larger, they come together, they make one big plate, they break apart, where more heat comes up and pushes them apart. So this has been going on over the entire history of the Earth. Okay, so this is a map of the Earth showing where heat is coming out, a distribution of how much heat is coming out. So heat is coming out more at places where this hot material is coming up and pushing plates apart. And on continental land masses, that's where the least amount of heat is coming out. Okay? So if you look at the magnitude of heat that's coming out in milliwatts per square meter of surface area, how does that compare to the heat coming in from the sun? Does anybody have any idea?
It's always a magnitude. I think it's like 1,000 watts per meter squared from the sun.
From the sun, exactly. So we're looking at about 100 milliwatts per meter squared coming out of the Earth. But remember, the core of the Earth is again about the same temperature as the surface of the sun. Okay. So over the 4.6 billion years that the Earth has been in existence, the formation of these plates, the loss of heat, has generated the tectonic plates, which have been constantly changing. The escape of heat, loss of heat, has created the oceans and the atmosphere, and in particular I'll talk about water and oxygen. It's created different types of rocks, three main types of rocks, which are igneous, metamorphic, and sedimentary. Somehow life started to form on the Earth and evolve, and it's created our main source of energy today that we still use, which is fossil fuels, and also all of the other kinds of ore minerals that we need for alternative or renewable technologies. Okay, so plates form and then they sink, and where they sink, also where they form, where the hot material is coming up, and also where they sink, you tend to have volcanic activity. And volcanic activity is shown on this map here. Volcanoes across the globe are shown as these red dots. Okay. So there are volcanoes that occur in the middle of the oceans, but most of the volcanoes are occurring where one plate is cooler and it's sinking beneath another plate. Okay. Water that's in this part of the rock comes off, melts these rocks at a lower temperature than they would normally melt at, and you have a volcano. What's coming out of the top of the volcano? Besides the magma and the lava. What's this stuff here? Ash or steam?
Sulfur dioxide.
Other gases? Okay. So that's actually how the atmosphere of the Earth started to form and evolved in part. So initially the atmosphere, what was coming out was mainly hydrogen and helium, which was out there in space too. As the volcanic activity started to evolve and occur to a greater extent, the volcanoes started to release water from deeper in the planet, things like hydrogen sulfide, carbon dioxide, some methane, ammonium, even phosphoric acid gases. Okay. And over time, as life evolved, the additional, what was added was oxygen and nitrogen, okay, for the most part. Okay. So let's focus in on the water and the oxygen, because those two components of the atmosphere are related to life and are related to our fossil fuels. So where did the water come from? Well, once there was enough cooling of the Earth, then liquid water was able to condense from water vapor. And that started very early in the Earth's history, about 4.4 billion years ago. We started to have water at the surface of the Earth. The oxygen, however, didn't start to form until about 2.85 billion years ago, when life forms, cyanobacteria, sometimes referred to as blue-green algae, but not really, but cyanobacteria started to make oxygen, presumably by photosynthesis. There were some life forms back here, but they didn't use the sun to live. They got their energy from rocks and minerals and hot water. So they started to make oxygen, and initially they were just making a little bit of oxygen, and the oxygen was absorbed by the water, by the oceans. It just went back in and dissolved in the oceans, or by the rocks that were on the floor of the ocean. And then as more oxygen was being generated, there was more oxygen being produced, more organisms were living, there was more oxygen being produced, and the oxygen started to be absorbed on land and also to form the ozone layer. And then finally, about around little less than 1 billion years ago, life forms really started to take off, and there was so much oxygen around that it was kind of saturating the ocean water, saturating the ocean floor rocks, saturating the land, and now there was enough to go into the atmosphere and make oxygen in the atmosphere. So we see that the concentration of oxygen in the atmosphere jumped up, and in fact at one point it was higher than it is today. And we're back down here today at about 20% oxygen. And the green and the red lines just show you the range of uncertainty and what we think the oxygen content of the atmosphere was. Okay, so once we had oxygen and water, we could start adding the third rock to the rock cycle, which is sedimentary rocks. Okay. So the rock cycle is just the idea that you can take any rock and transform it into another rock. But if we take any rock that's at the surface of the Earth, the action of rainwater, ice, and sunlight and oxygen will break apart that rock into small sedimentary particles that get transported down mountains, through streams, into the ocean, and get deposited in what we call sedimentary basins to make a sedimentary rock that gets buried over time. And sedimentary rocks are the main rocks that we find oil and natural gas in, so that's why they're important. Okay, so let's just take a moment and look at some of the fossil fuels that were evolving in this very recent part of Earth's history, say in the last 500 to 600 million years ago at most. And we're going to focus in this example on plants and when plants first started to form. And plants are the origin of what fossil fuel? Land plants are the origin of coal. Okay. So, about 420 to 360 million years ago, this is what the surface of the Earth looked like in terms of the distribution of tectonic plates. So the brown are land, exposed land. The light blue is very shallow seas on the margins of the plates in the land. And then the deep blue is the very deep ocean. So this was the distribution of the plates. And these plates were starting to move together to form a big supercontinent that we call Pangea. And that happened in about 360 to 300 million years ago in a time that we call the Carboniferous. Okay, hint. So there were a lot of swamps with a lot of land plants, and the land plants were evolving rapidly then. And this is what the North American plate used to be, right here. Okay. And when these other plates started to collide with it, all right, there were a lot of swamps bordering the side of the plate. And look at the position of the plate in terms of the equator. Okay, so it's in a warm part of the world, lots of swamps, lots of plants. Plants are dying, they're building up, making big layers of organic debris. And out in the oceans, out in all of these shallow light blue areas, there are phytoplankton, small organisms that are also living, and they're going to die and sink to the bottom and make layers of their remains are going to make layers mixed in with the sediments that are going to become oil fields. Okay? So we have coal and oil forming. And so these are the plants, these are the phytoplankton. Let's see, what else do I want to... Oh, yeah. Okay, so let's zoom in here for a sec. This is the collision of two plates. What happens when two plates collide? What do we make? Mountains, right? They bang into each other, material goes up, we make mountains. Then we have volcanoes that are effectively mountains too. So once there's a high point on the surface of the Earth, you have water and oxygen, precipitation, raining down on this high mass of Earth material. What's going to happen to it? It's going to break apart, erode, become sediments, okay, make sedimentary basins. So, mountains, you need high topography, the interaction with rain and oxygen, breaks apart the rocks to make sediments, they flow down, they make sedimentary basins. And that's where all of the organic material that's living and dying is ending up at the same time, mixed with these sediments. So if we take a look at the U.S., for example, today we see the Appalachian Mountains, which, by the way, were being formed in that yellow circle at the time that the swamps and the land plants were growing. That high topography there is the Appalachian Mountains. And out west we have a lot of mountains today. And if we look at recent basins just in the U.S., all these circled outlined areas are places where sediments are being deposited and filling in low-lying areas relative to high areas. And if we look at the distribution of coal today, okay, any of the yellow, green, and gray areas are all coal deposits. The different colors represent different ranks of coal, or how much carbon is in the coal and how much energy you can extract. So the highest ranked coal are the grays, okay? The lowest ranked are the yellows. Okay? But all of that coal, think back, all of that coal was at one time a swamp near the equator on a plate that had a different shape and a coastal outline than it has today. So at the same time that the plants, and actually before and up until more recent times, both things have been going on, not just 300 million years ago. But out in the oceans, the dead organisms were dying and sinking to the bottom and getting buried in sedimentary basins. And a sedimentary basin is shown up here in a cross-sectional view. So here's a layer of sandstone, and this black layer below is shale. Okay, and this is some kind of shale up here. But the sandstone is a rock made of sand grains that have been compressed together, and there's spaces between the grains. So the oil and natural gas comes out of the shale. It's typically buried in with the mud in the shale. It gets buried deep enough to a high enough temperature. The remains of the organisms convert to oil and natural gas. They somehow get squeezed out of the shale, rise up, and get trapped in the sandstone. And because oil and natural gas are lighter than water, they keep rising until they get to a place where they can't go anymore. So some kind of seal on top, and that makes an oil field. Right? So now it's just a matter of the oil companies going in and finding where these places are, where there's a concentration of oil or natural gas. And the gas typically sits on top of the oil. Well, will sit on top of the oil because it's less dense. So over here we have a representation going from the sugar that Professor Hoffman talked about. Increased temperature and pressure, it converts to oils and natural gas. We have methane, ethane, propane. The next one would be butane, which was in the letter. Okay. So normally, the oil and natural gas, if you punch a hole in these rocks, the pressure will be high. Either the pressure will be high enough that it will just flow out by itself, or you can start pumping it up. Okay? But today we're looking for the oil and gas in the shales directly. The stuff that hasn't gotten out into the sandstones where it can pool and form a big field. Okay? And that's the oil and natural gas that we're trying to get out by hydrofracking, hydrofracturing the rock. Okay? Everybody know what hydrofracking is? What is it?
Horizontal drilling and then injecting water and diesel fuel, among other things, to break the shale up and release the gas.
Right. So it's somehow putting a high pressure, I think maybe even explosives, I don't know, but they fracture the rock, and that allows the oil and natural gas that's caught between the pore spaces in the shale, where the grains are much tinier than the sandstones, to escape out, okay, and be pumped out and collected. So there's a huge amount of oil and natural gas in shales that underlie, say, a typical sandstone where we get normal conventional gas and oil out of. And again, those shales are distributed in these basins, these sedimentary basins. So just looking again at the U.S. Okay. So right now, the Bakken Shale up in North Dakota is a really hot spot. It's a place of a lot of economic activity, and this is part of what the Keystone Pipeline Keystone Pipeline's being constructed in part from Canada, but also would carry oil and natural gas down from the Bakken Shale to the refineries that exist all along the Gulf Coast. What's one of the main environmental concerns with fracking? Does anybody know? Methane release that gets into the water supplies in layers of sandstone that are higher up that contain the water that we know. Okay? So some people in some places, I think particularly in the Marcellus Shale area, have been able to light their faucets on fire because of the methane coming out. The other thing it can do is the fracturing can release a lot of toxic elements from the shales that get into the water supply. I have no idea of my time anymore. Okay, all right. So, that's kind of finishing up the fossil fuel part. Any questions? Okay. So now we're going to move on to mining and how that's related to the earth and tectonic plates, and also to critical energy, or advanced energy technologies. So there's a certain set of elements that are referred to as energy critical elements, and some of you may know what these are and be working with them already. And they're needed for various high-tech materials, such as photovoltaics, electrodes, superconductors, catalysts. And here's a part of the periodic table highlighting some of them. And they include elements called platinum group elements, so platinum, palladium, which are used in catalysts. They include a group, gallium, indium, and tellurium, which are used to make thinner and more flexible photovoltaic materials. The rare earth elements, I'm sure you've all heard of the rare earth elements. Are the rare earth elements rare? No. But they don't occur, typically, they can be concentrated, but even when they're concentrated, they're usually kind of dispersed through an ore matrix. Okay? They're everywhere. They're important because they have lower mass and size. They're important because when they're used in magnets and motors, they make the motors weigh less, okay, and be smaller. They're also used in phosphorescent lamps and in catalysts. And then a group that are critical for battery development: lithium, nickel, cobalt, manganese, for example. These types of mineral resources, just like oil and natural gas, they depend on the geology, which varies across the globe, which depends on how the plates have moved over the Earth's history, and they're very much influenced by geopolitics. Right? So today, even today, China is the largest source of rare earth elements in the world. They are mining the most rare earth elements. They have the market cornered on rare earth elements. So this is an issue in terms of geopolitics. Here you see the distribution of mining of rare earths over time. The U.S. is the blue, China's in the red, and other countries in this kind of orange. Okay. So how do we deal with this? Well, look, there's a lot of rare earth elements in the ocean. All over the ocean floor, there are things we call manganese nodules, shown down here. Very small things, kind of hand size or smaller. They have a lot of rare earth elements in them. Great, so we can just go start dredging up the ocean floor. Well, who owns the oceans? Right? So let's say you've got a big manganese nodule deposit off your coastline. Are you going to be able to go out and start dredging it up and make money off of that? Huh? Question? Okay. And then all the other places that have high concentrations of these kinds of energy critical elements and other elements that we need is the African continent, in particular the southern part of Africa. So the Congo is one country that contains all sorts of very valuable elements, uranium for nuclear energy, for example, metals, manganese for batteries, for example. It has a lot of coal, it has iron ore. So let's take a look at mining in one of these countries and what it really means.
This is illegal in Russia. To summarize this, it's an illegal timber line. Didn't even get for the forests. No roads in the mine. The only way to get there is to walk 30 miles along a narrow and windy foot. When I made the trek, dragging rain showers hit you in the soil underfoot into a slippery slide. At the end of the path, 10,000 people live and work in extraordinary squalor. In the makeshift village that sprang up around the mine, workers live in mud huts covered with plastic sheeting. An open-air slaughterhouse sits beside a river, where workers bathe and wash their clothes. Because of the remoteness of the village, and the fact that the militiamen who control the mine take a cut of every income, life here is expensive. A bowl of rice and beans costs 6 times what it does elsewhere in Congo. A mud hut can rent for as much as $50 a month. Up on the mountain, the search for tin ore, known as cassiterite, goes on day and night, in hand-dug tunnels as deep as 600 feet. There's no electricity and few modern tools. Toxic gases accumulate underground and tunnels cave in. In the open pits, tropical downpours bring mud cascading down on workers. Soldiers are always present, ready to seize their percentage of the mine's production. Tin doesn't have the dazzle of diamonds or gold, but outside the jungle, smelters will turn these ochre-tinted bits of rock into solder that is essential for laptops and cell phones. The only way to get the ore out is the way workers came in. Porters are paid about $40 each to carry the heavy stones back to the main road. Many build rudimentary backpacks from sticks, cloth, and string. Others simply carry the 110-pound sacks on their backs, supported by slings across their foreheads. At the main road, middlemen buy the ore, as much as $100 million worth a year. It is then packed into Soviet-era cargo planes and flown to the regional capital. From there, it is shipped off to a world market hungry for tin. It is the saga of much of Africa's riches. Unearthed by the poor, controlled by the strong, and consumed by a world oblivious to its origins.
So, even if we go, which we're going to have to do, go to all these renewable energy technologies, we need to think about where all the chemical components are going to come from that are critical for those technologies. And again, it's a matter of the geologic history of the Earth and combined with the current state of the Arctic across the globe. And then locally here, I know most of you are not from Illinois, right? Who's from Illinois? Oh, okay, fair number. So locally, we have a nice little hilly area where the Illinois River and the Fox River meet. And there's a nice state park called Starved Rock State Park, but it's made of sandstone. Same kind of sandstone that holds the oil and natural gas across the globe. And it's a really clean white sandstone, okay? The grains are big, there's lots of pore space between the sand, it's very clean, not much iron. And it's perfect. It's perfect for use in this whole hydrofracking business now that's built up to get oil and natural gas out of shales. So it's pumped down in with the fluids, whatever kind of fluids they use to fracture the shales, and it goes into the fractures as they form and keeps them open. So it's called a proppant. And as a result of this huge expansion of this business, this industry in the U.S., large regions of Illinois, especially around this very nice state park area, are being bought up and being strip mined for the sand, because the sand underlies all of this area where it's blue. Okay? So this is creating a lot of local problems and issues in this part of Illinois, and it's happening in Wisconsin as well, because the formation of sandstone extends up into Wisconsin. And I just saw something recently in the news that the oyster industry in Oregon is being affected. That's I'll get to that one next later. Okay, so that's all interior of the Earth, heat coming up. Okay, plate tectonics makes the fossil fuels and decides where they're going to end up, and also the ores. So now let's talk a bit about the surface of the Earth. What's going on there? Well, we have the sun that's heating the surface of the Earth. And at the surface, in order to keep the global temperature stable on average, whatever heat comes in has to match whatever heat's going out. So we have to keep the heat that's coming in from the sun matching whatever heat is coming back out of the Earth. Okay. So here's a picture of the Earth, and this yellow arrow coming in is the sun energy, and it's coming in as shortwave radiation, and it's unevenly distributed. What does that mean? Where's it coming in at the highest intensity? At the equator, and the least intensity at the poles. Okay. So the average incoming solar power is 1,387, about 1,000 watts per meter squared. And once, the incoming solar power here, and then if you average it over the whole Earth, at the top of the atmosphere, you have about 300 watts per meter squared. The heat that's coming out of the Earth is long-wave radiation. It's more uniformly distributed, okay? And heat is also reflected from the surface of the Earth. So the incoming heat is absorbed by the atmosphere and the surface of the Earth, and about 30% is reflected back off by the clouds and the actual land surface. And so the total average of incoming heat minus what's reflected and given back off is about 240 watts per meter squared. So a bit lower than the average. Heat that's absorbed in the lower atmosphere is emitted downward to the surface as radiation, okay, here. Heat absorbed at the surface is emitted upward. And this constant transfer, right, motion of this heat up and down is uneven over the surface of the Earth, and it's what causes the atmosphere to circulate and is related to what causes the oceans to circulate. And if the atmosphere is circulating and the oceans are circulating together, they are causing our climate. That's why we have climate, because the atmosphere, air is moving around in different patterns and the ocean is moving in different patterns. So here's a picture of the way the atmosphere moves and why it moves. So the atmospheric energy flow. It's basically the idea, if you heat air, it rises. Once it gets high enough up, okay, so evaporation uses energy. Once it gets high enough up, the water that's in the atmosphere starts to condense. That emits energy. You have clouds, rain, and snow, and it gets colder and it falls. Okay? So if you look at the surface of the Earth kind of in cross-section, you see that hot air is rising at the equator, the red arrows. This indicates a lot of rain coming out as it's rising. And then it cools down, it flows north, comes down around the region of the deserts, regions where there are deserts, and flows back along the surface of the Earth and cycles this way. There's a similar cell set up here for the atmospheric circulation, and then one right at the poles. Okay. The combination of the vertical cycling of air in the atmosphere with the rotation of the Earth, which is which way? Left to right or right to left? Which way is the Earth rotating in the picture? Left to right. Okay, so the Earth is rotating this way. So the combination of that, which creates the Coriolis effect, okay, sets up, and these cells sets up wind patterns on the surface of the Earth that are indicated by these arrows here. So this is the general direction of the winds. So for example, up here in this mid part, we have the westerlies. So westerly winds are called westerlies because they blow from the west. They blow to the east, but they blow from the west. Okay. All right. So the vertical atmospheric circulation sets up wind patterns on the surface of the Earth. The wind patterns on the surface of the Earth then actually drive the surface currents of the oceans. Think of it simply that way. And in addition to then the water in the oceans at the surface flowing around, I'll show you how that works in a second, the temperature distribution over the surface of the Earth causes differences in the temperature of the ocean water over the surface of the Earth. So it's colder at the poles, warmer at the equator. And that also then sets up a vertical flow of the water. Okay? So we have vertical atmospheric circulation. Then we kind of have if you think of it, horizontal wind circulation, which then circulates the surface water of the ocean, which then also circulates vertically. Okay? So all of those things are linked. And this is a picture of the surface currents, and for example, the one you might be most familiar with is the Gulf Stream, which carries warm water from the tropical regions up around the eastern coast of the U.S. and is responsible for the warm climate of Europe, which is actually at a higher latitude than we are. Okay, and then it cools down and comes back. So there's 5 main surface gyres, we call them, in the ocean. And the deep currents, okay, are a little more complicated. So they're represented by this, which sometimes is called the thermohaline conveyor belt, I think. And the idea really is that cold water is sinking in cold regions. Okay, so it's sinking up here, flowing very deep along the bottom of the ocean, and then at some point it comes back up and flows, not as a surface current, but below the gyre surface currents. And in that way, all of the oceans are constantly being mixed, but on a much longer time scale than any type of surface current, okay? Or wind pattern for that matter, which is much shorter time scale. So the oceans are being mixed on 1,000-year time scale, basically. but they're all mixed. All the water's moving around. So a droplet of water here at some point will end up over here. And the deep circulation is what controls climate over the long term. Okay, so fast view of the Earth, and heat from below, heat from above. And I want to just touch upon some implications for the use of energy, or our need for energy and the use of energy. And really, you know, it may look like an exaggeration, but it's not really, right? We could have a failure of our life support system if we're not careful and we don't do something about it. So obviously, you know, we're increasing greenhouse gases, CO2, as Professor Huffman just talked about, combusting fossil fuel, and actually methane is escaping now too. That's contributing. That's causing changes. The temperature is changing, and that's causing changes in the way the atmosphere circulates, which is then causing changes in the way the oceans circulate. And this is a big issue. We don't know, we cannot predict how the ocean circulation is going to change. But that's a big uncertain. Whoops. We're putting more CO2 into the atmosphere. CO2 dissolves in water and it makes carbonic acid, which lowers the pH of the water. And a lot of the creatures that live in the water that have shells, they make their shells out of a mineral that once you lower the pH, it starts to dissolve calcite. So their shells are dissolving and they can't live, they're dying. And this is the political issue that's just come up in Oregon, just in the past week, that oyster production is declining because the oysters aren't living. We're contaminating the air, water, and soil. We burn fossil fuels, we're putting things into the atmosphere like mercury, we're making acid rain. We mine minerals, and mining often involves digging out minerals that have sulfide in them, and when you expose that to the oxygen, that reacts with rainwater and oxygen and makes acid. It makes sulfuric acid, basically, in our water. And we're also, in all of this, we're depleting our known sources of fresh water. Fresh water is used for fracking, for example. That's one of the big concerns for fracking. So let's just take a quick look at water. I'm about to wrap up here. But water is helping to regulate the Earth's temperature, right? It's a part of the atmosphere. And it also regulates our temperature. And how much water are we? What percentage of the human brain is water? What did I hear? 90? 70? 60? Who has a brain made out of something less than 60%? We'll find out in 2 weeks now. 75%, okay, of the human brain is water. What about a tree? It doesn't have a brain, so maybe that's more. 75%, basically, okay? So organisms are 75% water. How long can you live without food? 3 days? A month? A week? 5 days? Maybe it varies from person to person. About the average person will live for about a month without food, right? About how long without water? You can actually survive for me. You're not going to be, you know, rain. That's why you should drink a lot of water. Okay. The amount of water on Earth today is what percentage of the amount that existed when the Earth first formed? 100%. Okay. So all the water that was there when it first formed, it's been redistributed. Now we have oceans, and now there's some in the atmosphere. It's the same total amount. And actually, people are saying that there's probably the equivalent of at least one ocean's worth of water molecules still down in the Earth, tied up in mineral forms. Okay. It's recycled. Okay. You may have a water molecule in you that was once in a dinosaur. So, obviously water is interconnected, right? It's being recycled all the time. Professor Hoffman showed us the cycle picture earlier. Here's another picture. So right now, we're messing with this part of the system, right? We're messing with the climate. We're messing with the amount of water that might evaporate, where it goes, when it forms clouds, when it rains back down onto land, okay? And where that happens. We're also messing with, potentially with the water that we drink, that we get out of the ground, by taking water out for fracking, by the population increasing and we need more water to irrigate agricultural fields, for example. And in the central part of the U.S., there's a big, what we call an aquifer, a big layer of rock, again sandstone, that holds the water that we use largely for irrigating the breadbasket of the U.S., okay, called the Ogallala Formation. 27% of all the land that our agricultural land in the U.S. Uses water from this formation. It's also being tapped heavily for fracking purposes, and we're basically taking the water out much faster than it would go back in naturally. So we're depleting this natural freshwater resource rapidly. So where's the closest source of fresh water that's not in the ground? The clouds. Well, where are you guys now?
Great Lakes.
Great Lakes. Okay, so Great Lakes are a huge source of fresh water, and they really are going to need to be protected in the future, especially as drought happens more and more in the West. I think it's going to start being eyed as a source of water. Big pipelines, huh? Okay. And my last slide. Okay, so I want to wrap up. Heat from inside, heat from outside. What is this? Fukushima, okay? Right? Japanese view of it. Let's think about this. It's an energy collision in some sense. How could we have avoided it? Well, why is it even there? We have nuclear energy because the uranium that's in the ground that's eating the earth and causing it to cool off over time, right? Earth is cooling, but it's the source of heat. Has created the plate tectonics and the different rocks and concentrated the uranium in ore deposits, and it's been extracted and used for nuclear energy. Concentrated further with the most radioactive version to use for nuclear energy. Okay. At the same time, all right, that heat loss generated by radioactive element decay created plate tectonics, created mountains and oceans, earthquakes. Two plates collide, they make earthquakes, which is what happened in Japan. The earthquake, when it occurs under the ocean, it's moving the rocks, right? And it basically moves the water up. And now the water wants to flow by gravity towards the land surface where the elevation is lower. And that's what a tsunami is. So that's what caused the tsunami in Fukushima, which flooded the reactor, cut off the electrical backup system to keep it running, and then also caused physical damage to have it leak and contaminated the water and soil. That's it.